Okay, all right. So if you've ever had basic soils, this is basically going to be an overview of the same stuff, more from my perspective. Just some considerations before we get started, what I want you to think about as we go through this presentation. There's a couple things about soil water in agriculture. We're thinking about things like infiltration, because we want water to enter our soil so it can be stored for plant uptake. Conductivity, because once it gets into the soil, it has to be able to move through. We don't want it ponding or sitting in there. And then storage is also important, because the more water your soil can hold, the better your plant growth is typically going to be. So all of this occurs in soil horizons, so hopefully you've had some basic soil horizons. We'll talk about it a little bit. The important things about soil horizons is that they're made up of soil mineral particles and organic matter, and what they contribute to water holding is going to be that CEC, which gives charge and holds on to water, and also the building of structure, which gives us these macropores. So if you've ever thought about horizons in terms of water, we've got two things we talk about. Infiltration, water has to get into the soil, and in conductivity, it has to move through it. So that infiltration is going to be right at the surface. So typically that A horizon is where you're going to have infiltration. It's going to have storage. It's going to have some storage. But mostly that's what we're concerned about is infiltration. And that's the one you can mess with the most in terms of compacting it or getting rid of good structure, which allows water to enter that soil. And then we have conductivity and storage down in the B horizon. So this can be these layers that might prevent water movement, but it's also where we get a good amount of water storage. Often when we take our soil samples for nutrients, we look at that upper 6 to 8 inches, but we forget that all that good water storage, because your roots do get down deeper, that's a lot of where your water storage can be later on. And then if you know anything about the C horizon in ag, most of our ag fields, the C horizon is probably pretty deep. If you have a C horizon near the surface, it's not typically a good soil to grow anything on, so we can kind of ignore it. It's not going to have a whole lot of water holding capacity depending on the soil type. So typically the A and B horizon, if you're looking at your soil survey, are where you want to look first in terms of infiltration, conductivity, and water holding. So we have some different pictures that I stick in almost every presentation I do on soils. But in this case, for these horizons, that one on the left, here's something that has straight C horizons. So that's a sand dune. You don't usually grow stuff there much. But this one right here has stones in the layer, where it's an alluvial soil. Well, stones don't hold a lot of water, so you don't have water storage. Water might move around them easily, but it's not going to store a lot of water. A plow layer right there where the plow's gone through, that's going to affect how water and roots can move through that layer right there and limit conductivity. Saturation creates certain soil horizons, but if you have a saturated horizon, then water can't drain off, and that's also going to affect how plants grow. And then, of course, shallow bedrock, if you're from the other side of the bay, you have to deal with this a little more. That bedrock layer is going to limit your total storage in the soil, and it's also going to limit where water can move to. So it's very important to think about that subsurface horizon. In terms of fertility, we always think of that surface. But if you look at your survey and you check those subsurface horizons, this is a project that's from 20 years ago, and you can see where we have poor plant growth here and good growth here. This is the Bojack. It's a sandy soil that only got 85 bushels of corn that year. The Wickham got 160 bushels of corn. It could hold 7 inches of water. The Bojack held about 3.6, and it was all because that subsurface horizon had a little bit more clay. So that water storage becomes very important when we talk about soil texture. So when you talk about texture, you got to back up in and understand the mineral particles in a soil. We pretty much decided that everything less than 2 millimeters is soils. Everything bigger than that is a stone. And when you split up those particles, sand is the largest, 0.05 to 2 millimeters. Silt is pretty much there to break up sand from clay. And then clay are our smallest particles, which you really can't see, but I have to put an image up there so you can kind of get an idea. And it's really important to talk about these because they affect a lot of your water storage and what we're going to talk about in terms of textural porosity. I'm sure you guys have done this before, but if not, you can look up the textural triangle. If someone gives you a soil texture and you're trying to figure out the different percentages, you can use the textural triangle to at least back out the range in these particle sizes that we have in there. But if someone says you have a 70% sand, you draw that line, you look at where that arrow goes, you draw the line across, silt, draw it down, clay across, and it's going to tell you that that's what we're calling, in that case, should be a sandy loam right there. Yeah, so we have a sandy loam soil. So if you want to know what possible ranges of soil particle sizes you have in your textures, you can look at the textural triangle. But in general, these textures will give you an idea of what might happen with water storage. And so the reason that's important is what we call textural porosity. This is something you can't change in a soil. You can compact any of these particles so tight, and you're still going to have some pore space in there. You can only get the particles so tight together. So if you look at how we've drawn this sand, silt, and clay there, you'll notice that in the sand, you have one very large pore space. When you get down to silt, you have more pores, but they're smaller in size. The clay, you can't really see them. So while those clay pores might get incredibly small, and if you think about straining something through there, this is going to slow water movement. But what you can't see is all those tiny particles. If you made all of this clay the same size as that sand, all those tiny pore spaces add up to more total pore space. So this is where we have to start thinking between, are we concerned about drainage or are we concerned about water holding? Because that sandy soil is going to drain very quickly. But it has less overall total pore space, so it doesn't hold as much water. This is something that you can't change in the soil. If you understand it, you can talk to people about this is why you might be having these problems with these different soil types and these different textures. You can't change your textural porosity. It's just a property of the soil. What you can change is your structural porosity. So soil structure is how all these particles form shapes in the soil. All these names for soil structure are after the shapes that we see in them. A blocky structure is not going to look like a perfect block in most of our soils like this, but this is a good picture, so I always show it. So the nice thing about structure is it adds pore space to your soil. You can't necessarily always see or tell it's there, but that's what it's doing. If you look at what we call the ped face on the soil, this is actually soil from California. These are carbonates that have accumulated on the surface. The only way they're going to accumulate on the surface is if they can move through there with water, either through evaporation carrying it up, rainfall moving something down. So if you see coatings on a soil, you're actually seeing pore space where water moves through. And I'll show you some pictures, but we're used to thinking of pore space as the biological pores, like earthworms and root channels. Those are easy to see. But a lot of your pore space, a lot of where things move, are actually along these cracks in the soil. So these are some of the shapes that you could possibly see in a soil. If you have a forest soil or you've had pasture for a while, you might see these granular shapes. They're more like spheres. They're associated with high organic matter. We don't typically see a lot of it in our ag soils anymore, especially if we have tillage. You can definitely see it in the forest soil. You can definitely see it in your lawn along the roots if you dig it up. It's very easy to see in that case. Blocky is the most likely shape you'll see. It's hard to describe. Sometimes it's hard to separate out massive from blocky structure. It just takes a lot of experience in going out into soils and breaking it up. You have to be good at lightly breaking up soil to see if there's structure there. That's a whole other class to even get into something like that. But blocky are these square shapes. And if you think about something like quartz, and you've ever looked at the planes on quartz in your geology class, when you break it down, it always breaks on the same planes. Well, quartz is silica. Most of our clay minerals are silica. So soil likes to form these blocky shapes. It's just like quartz. It's going to build these mineral shapes that follow the same structure. It's a repeated crystalline pattern in soils. You can also have massive or cloddy. Massive is usually going to be associated with rock structure or that sea horizon. The clods under the NRCS is more what we associated with a compacted soil due to our practice in the field, our management. So a clod is going to look like a block, but it's going to be a big, jam-packed piece of soil that doesn't have a lot of pore space in it. And then there's also in the sands, because we're on the coastal plain, we have to talk about single grain structure. If you don't have a lot of clay in your soil and it's almost pure sand like the beach, it doesn't stick together into shapes very well. We call that single grain. Most of our fields that we're farming shouldn't be like this. So what structure adds between all those shapes is the structural porosity. Once you take, if you have a mass or a clod, and over time it's going to separate into these shapes, it wants to form these shapes, what you add is this additional pore space in between it. You add larger pore space in there. You add what we call structural porosity. So sand, silt, or clay, whatever's in your soil, you can't change that. You can't change the textural porosity, which is a lot of your storage. What you can change is the structural porosity, typically through things like no-till and building organic matter up. And that is going to be your drainage component that's going to allow water to move through when you have a high rainfall event. So the thing about soil is it wants to stick together. Soil wants to bond to itself. So we have a tilled soil right here, and after it's rained and dried back out, you already see those cracks forming. Now, it's going to be very weak structure those first couple of years. You can break it up with your hands very easily. You can break it up with raindrops. but it's still there. Soil wants to stick to itself. It has a charge. It wants to bond together. And it will do it if left alone. And it will do it immediately. Shrinking and swelling of soils, freeze-thaw cycles, all those things help add some of the structure to your soil after you've broken it up. The point is, how do we keep it glued together and keep it stronger? And those are things like organic matter and glomalin from roots and things like that. So you see in this soil, we have at the surface, still there's not a lot of organic matter. It's not a dark-colored soil. But you can see where we've gone through in all these different blocky-like shapes. They're not massive clods. They're these blocks that are at the surface. There's not a lot of organic matter, so it's not granular, even though we're leaving residue. But between all those blocks is where water can move through the soil and infiltrate. So this is at our research station at Carville. You can see this is a tilled soil. We have very sandy soils. So every soil is going to have, depending on its texture, how it reacts to compaction is going to be a little different. But here's an irrigation track. And this is a structure I didn't actually show a picture of, but this is where you can get platy structure in our areas by compacting it very hard. So all I did was stick a spade in and dig it up, and you can see that layer right there. How are roots or water going to move through that when you have a flattened out piece of soil? Now our soils are sandier, so water might move through them faster than clay soil. So the texture of your soil is going to control how well water moves through it. But we still end up, and you'll see it, we'll still end up with ponding on our soils without good structure in it. And over here, the same thing. You'd see it from the side. There's what we call that platy structure. It's been compacted, and it still has the textural porosity. We can only get it packed so tight together, but it's missing that structural porosity. So the thing, if you've ever heard of a tortuous path, it means a path it's longer, it's hard to follow, it goes in different directions. If you have a macropore like those cracks, water can move straight along that path. So here we have a little bit of structure reforming at the surface. So along these cracks, water can move. But down in here where it's all broken up, how's water going to move through that tilled soil? It's going to have to move whatever direction it can get around all those particles to move through. So it ends up building up, and it doesn't move through it very easily. What structure adds is these direct paths through the soil. So you might not see this easily because I was trained as a pedologist, and we had to dig in a lot of pits, and I had to break up a lot of clods and look at a lot of structure. I can tell when I take a soil and gently break it apart. You can see maybe clay films or a face. When you break a soil very gently with your hands and you see these shapes going into it like this one does, this little indentation right in here, that is, and this soil has only been under no-till for 1 year, and it's a sandier soil, so it forms the structure a little bit easier. But we have this face along here, and that's where your water and roots can move easily. They can push through a sandy soil. You see this root down through here, it's moving through, but more than likely it's going to follow that path as it moves through. So you might not see where those pores are in your soil as easier as you'll see the biological pores. That's what we're used to talking about. We talk about it a lot in soil health, but you're going to have pore space in the soil that's no-tilled even without earthworms. It's there. The soil's going to form that structure on its own. So if you look right here, you see all these holes in the soil that can be from roots, they can be from earthworms. When we talk about pores, that's usually what we visualize. There's round pores that are very obvious. And they do the same thing, except unlike that structure that might break up the soil in these shapes and have a straighter path, that earthworm or root might have a more tortuous path. But it's still, the point about those is they're larger. We're talking about like sand. The larger that pore is, the easier it is to fit water through there. So what we have to always remember with soil and water is that they both have charge. So we all know, right, that soil has cation exchange capacity, that soils are dominantly negative in charge. Well, water has what we call polarity. If you remember hydrogen bonding from your chemistry class in high school, which is, 25 years ago now for me, water has polarity and hydrogen bonding. What it means is oxygen is more electronegative. It likes to hold on to electrons a little more than the hydrogen. So oxygen is actually a little bit more negative than the hydrogens. So what's that going to do for your soil? If your soil is negatively charged, then those hydrogens are going to be able to bond to that. It's not a strong bond, but it's better than nothing. It's going to help it stick to it. And also, water can stick to itself because you have the positive from the hydrogen can line up with the negative on the oxygen. So if you've ever seen those little bugs that scoot along the water and there's just a little indentation under their foot, you're seeing cohesion, where the water's sticking to itself, and you have to have enough pressure to break through that. And that's important in soils because now you can see that water is going to stick to soil and to itself, and that's going to help it move and be stored in the soil. So when we talk about water holding in the soil, the adhesion is where it sticks to the soil. The cohesion is where it sticks to itself. And then we also have these forces that are working against it. Plant roots are pulling on your water. Heat is evaporating your water, and then gravity is also pulling it down. But gravity is not as strong as soils are at holding on to water. It can pull some of it out, but it can't pull all of it. So the wider this pore is, that cohesion that's holding the water together, the closer you are to the soil surface, the tighter that water is held. The further you get, it's not held as tight. So the wider your pore gets, this water in the middle, it might be sticking to itself, but gravity's strong enough to pull that away. So your wider pores drain easier, and gravity can take over from what we call the matrix forces in the soil, that matrix of the soil that holds on to water. So this is why oftentimes when we talk about soil water, we use terms that are related to forces and energy. Because there's a force holding on to water, there's forces pulling on to water, so gravity, roots, or heat are all these different forces that are acting on water. So when we talk about movement through the soil, or movement to plant roots, or evaporation, those are all different forces pulling on each other. So when we talk about water holding in energy terms, if you go through your soil textbook, you'll see more terms than I put up here because I'm not going to talk about osmotic potential. Really, the one we need to know the most is pressure potential, and we're really concerned about the matrix, but I'll go through a couple of these. So water potential, if you remember the difference between potential and kinetic energy, the ball sitting on top of the hill has potential energy. As soon as it's rolling down the hill, it has kinetic. Water in the soil is held so tightly and moves so slow that it always has potential energy. Versus water in a river that's moving fast and it's undergoing kinetic energy. So that's why you hear the term water potential. There's all this potential for it to move, but it can't move easily. And it's held pretty much at a low potential. It has a very low energy. We split those potentials out into gravitational, because the higher it is in the landscape, the higher energy it's going to have, because gravity can pull it more. And then these pressure potentials. So matrix is the soil's potential to pull on it, and hydrostatic is pressure from the weight of water. And I only mention this because you have to understand why we might use the positive or negative when we're talking about soils. So we add all of these potentials together, and I'll point out down here at the bottom, I don't need you to memorize these names. If I don't talk about this for 5 years, I'll forget all the names too. It's perfectly fine. It's the concepts you want to keep in your head, the negative and positive when you're looking at these different numbers. So gravitational is very simple. The higher your elevation is, the higher the potential energy, right? Things want to move from high to low energy. So if you put something up on a hill, it wants to roll to the bottom, and that's due to gravity. So it's the same thing in a soil. If you talk about water in the soil here than here, we're going to say that water has a higher potential energy, and that's due to gravity. So the way things move in a landscape, that's how we can say it moves from high to low energy. Gravity is going to be part of that. So if you have a saturated soil up here, it can move down slope, so higher gravitational potential. Outside of that, because I live in Delaware and we don't have a whole lot of difference in gravity and elevation, it doesn't affect us as much. But it's really the pressure potential that we're concerned with. Because in agriculture, where are we growing our plants? We're growing it in these conditions. We don't want it to be saturated. So this is your pressure potential. There's matrix and the hydrostatic. So matrix is always negative. You'll always see these negative numbers associated with water in the soil. And that's because it's just like electrons and protons. You could switch the signs. It doesn't matter as long as they're opposite. But it makes more sense if you, just like when you go under the sea, and the deeper you go, the pressure builds up. It's the same thing with a water table. When you're saturated, the deeper you go, the more pressure you have above you, so the more positive it gets. So right here at this line, the water table, this triangle means water table, that's 0. So your pressure is going to be 0, just like sea level. So as you go deeper, it gets positive. So if you go the opposite direction, if you get drier, it has to go negative. So if you think in terms of energy, if you're going from high to low energy, where's water want to move? It's going to want to move from something that's wet to something that's dry. So soils that have a negative number, the more negative it is, the drier it is. But also it's letting you know that that's where water can move. If you saturate a soil, it's going to want to move to that drier area. So it's all about energy and forces and movement. So underwater holding, we have these 3 terms that you often use. One is saturation. Your soil is fully saturated and gravity can actually pull some out. Then there's field capacity. All field capacity means is you had a recent rainfall and there was enough time for gravity to pull out what it could, and that's all going to be different for every single soil texture. So gravity can pull more out of a sandy soil than a clay soil. But field capacity, if anyone says my soil's at field capacity, it's got the highest amount of water it can without gravity pulling it out. And then we have wilting point. That's the point where your plants start to wilt. Your plants can pull more water than gravity can. They can get right next to that soil. They have a potential to pull water out, but they can only do so much. Even when your soil feels completely dry in your hands, there's still moisture in there. You have to put it in an oven to dry it out. So that's your wilting point. So there's no plant access. So saturation is certainly where crops go to die, right? If your soil is fully saturated and you don't have any oxygen in there, they're not going to make it. So you want it to be at field capacity. Field capacity, depending on the soil, might not be great for getting equipment onto, but it's going to have oxygen in it for your plants, and it's going to have water in it for the plants. Wilting point is way too low, so when we talk about available water in a soil, it's between field capacity and wilting point. And the amount in every soil is going to be different. So this is where you get into these values. This is why I was talking about negative and positive, because you'll see these associated with water in a soil. If you're at saturation, unless you're going deeper in the water table, you should be talking about 0 kilopascals or 0 bars. Negative 33 kilopascals or negative 0.33 bars, depending on what units you like to use, that's typically field capacity for most soils except for a sandy soil, which doesn't hold it as well, and it's typically about negative 10. And then wilting point is considered to be about negative 1500 or negative 15. So as you get more negative, it's a drier soil. And where does water want to move? It wants to move from high to low. And I'm not saying it moves fast, but if you've ever looked at those videos of water moving through a soil, you saturate the surface and you see it moving through. Where is it moving? It's moving to the drier spots. It's the same thing in this case. It's not moving at lightning fast speed, but it is moving in almost all cases, even if you can't see it visually. It's moving across there. So how do we measure water in pore spaces? You might have heard these terms before, gravimetric and volumetric. Most of the time we're measuring gravimetric, which is just weight, because it's easier. You take a soil sample, you dry it in an oven, you measure the weight loss, and that's how much moisture you lost. So that's gravimetric. Volumetric's harder. It's about how much total volume of water. So gravimetric is great for a weight. Volumetric is more associated with the pore space that you have. And to get the pore space, you have to know your density. So most of the time, it's easier to report it in gravimetric, and then you do a conversion. You can guess the density. But if you want to be accurate, you actually have to measure your bulk density of the soil to get a good volumetric water content. So most of our volumetric water contents, if you have your bulk density and you multiply it by the gravimetric, then you can get your volumetric water content. And what's important to remember about this is volumetric water content, 0.53, 0.48, 0.35, it's never going to be 1. If the volume of your water is 1, that's 100%, and that's a lake. Your soils will never have 100% water. And your pore space in the soil, usually it can be between 30% to maybe 55%. The rest of that space in the soil, 0.53 here is water, and the other 0.47, that's your soil, right? So your volumetric water, if you ever look at one of these graphs, and you're like, why isn't it 100? It can't be. So then you might get into these water retention curves. And a water retention curve can be different for every single soil type. Has anyone ever calculated a water retention curve in here? Had to do it in grad school or undergrad? They probably don't teach that anymore. I had to do it at Virginia Tech. It's very intensive. You basically stick a soil sample in a pressure plate, and you apply pressure that's going to be equal to one of these levels, negative 100, negative 1,000, and it forces the water out. So negative 1,000, you put a positive 1,000 pressure, and it's going to push out the water. And that's how we develop these curves. You actually have to apply pressure or dry the soil out. And you do that for all these different soil types. And one way they would do this is they would grind the soil up and put it in a little circle and measure the loss that way. But it's not going to be accurate, because if you ground it up, you've lost your structural porosity. So if you've ever taken a bulk density core, one of those cylinders, if you stick that in the pressure plate, that's going to give you more accurate measurements of your volumetric water capacity. But this water retention curve, if you look right here, we go to about 54%. So that's the maximum amount of water volume in that soil that you can hold, 54%. And it quickly drops off in the volume as you get to drier soils. So that's all these numbers mean. So your negative 1,500 right here, that's your wilting point. There's your field capacity. So your soil drains quickly, and then everything between here, this volume of water, is going to be what's available to your plants. So then we get into pore size and water holding. If you start adding all this up, adding it all together. So the yellow on there, this is not very scientific. The yellow on there represents what I'm saying is how far the charge reaches outside of that soil. So if you have a really wide pore, the wider that pore is, the reach of that soil isn't as far, that charge to hold on to water. That's how I look at this. So if you have a very large pore, right along this edge here, you can wick water up so far, but you can't pull it up in the center because the charge isn't there, gravity keeps it down. The smaller your pore space is, this is that capillarity where you can have water rise inside of a soil. Like a water table, even though saturation is at 0, above a water table, water will rise up a little bit and fill that pore space. The same thing right here. In this case, I put these soil particles so close together that the charge overlaps. You can hold a lot more of the water in this case. So this is good if you want to hold water, but what about plant roots? How are they going to get access to something like this? So with roots and available water, this is why everything in soils, there's never a silver bullet, there's never one answer. You have to understand everything to know what's going on. If you have really wide pore space, almost all that water between there can be available to the plant root, but how long is it going to be there if gravity can pull it all out? So the wider your pore space is actually better for drainage, but it's not necessarily good for storage. You want water to enter the soil? Yes. You want water to drain through it? Yes. You want it to hold it and be plant available? Not as likely. Versus this one, the smaller our pore gets, the more likely it holds on to more total water. But this plant root moving through here, these red lines here represent the unavailable. It's bonded to that soil tightly. It's not coming off. It's aligned with the soil, and the plant root's not going to get it. So there's no one answer to this. So this is where we get into texture and water holding. And this is from the Basic Soils textbook. And I really like it because it gives you a good overview of what to expect and how texture affects overall water holding in a soil. So down here on the bottom, we have sand, sandy loam, all the way to clay. So we're going from a sandy soil to a clay soil. We have your field capacity right here. So water is drained off. Here's your volumetric water content. So this soil tops off. As you get to clay, it tops off here in this case at about 35%. And here's your wilting coefficient. So everything below the wilting coefficient is unavailable to plants. Everything up here is available to plants. So if you look at a sandy soil and you look across this whole range, sandy soils don't hold a lot of water, but almost all of it is available because those pore spaces are so large. So it doesn't hold a lot of water. You're going to lose it very quickly on a hot day. Plants are going to suck it up, but they can get almost all of it. But that's not necessarily going to make you feel better just because they were able to get 6 or 7% volumetric water in there. As you go across these textures, you'll notice, well, we can hold more total water. As those pores get smaller, we get more total pore space. We can hold more water. But what's coming up behind it, as those pores get smaller, it's also held tighter. And the reason, if you've ever heard that someone says that the loam or silt loam texture is one of the best for agriculture, a big reason is that pore space. So by the time you get to clay, you have the most possible total water held, but you also have the most highest unavailable water possible in this soil. So if you look right here, the maximum available water, total water available to a plant is going to be in these two textures. Well, what can you do about it? You're not going to go out there and change your texture. So you have to just understand where is good and bad water holding and see if it helps explain some differences in yield in the field. You can't change this. You can change your structural porosity, but I still think that pushes more towards drainage in the soil versus water holding. It can get water into the soil for holding, but it's not necessarily going to help with holding itself in most cases. So if you haven't had basic soils, then you haven't seen this test before. I haven't done it in about 3 years, so we'll see if it still works. So you take a sponge. You can do this at home. You can show it to anybody. You can show it to any students. Sponge is just like a soil. It's going to be able to hold some water. You stick it lightly in the water. you're going to see it wick up. So I just put it in about 1/2 inch, and it moved up 1 inch. That's exactly what a soil is doing. The water's sticking to the soil, and it's sticking to itself. So that would be your adhesion and your cohesion going on at the same time. And that's exactly what soil is for water. It's a sponge. It has pore space. And then you can soak it. So this is not always easy to pull off. Typically I squeeze it out some so it doesn't leak too much. Of course, if you squeeze it out, what are you doing? You're compacting it, you're losing pore space, so your soil's draining. It holds less total water. So this is similar to, we talk about pressure head. If you turn this up, you see it start to drain, that's your gravitational potential. Now you have a higher pressure head. You have more pressure on top, and gravity is able to pull it out. Turn to the side. So that's that gravitational potential right there. The matrix potential is how this can hold on to it, which I don't know what kind of charge a sponge has. It works somehow, but I don't know if it has charge like soil. Never thought about that till now. But here's your gravitational potential. So this is a really good example to show students about how soils hold water and how it wicks up. If you put this in dry, you can see it wick up through there, and you can talk about how water is attracted to itself and attracted to the soil and move up through. So that was an example in undergrad that really helped show me. Visual examples always help me in soils and understand what's actually going on and visualize what's going on in the soil. So what can you do about infiltration? We're talking about soil water holding some. And this gets to be a touchy issue depending on who you are. I already see, of course, soil scientists, we push back against soil health some. But farmers across the country pushing back against soil health because I see a lot of Twitter videos where they're just tilling their soils and laughing about it to people. But it's all about what you want to do and how you want to manage it. I never tell people tillage is right or wrong. I just say, here's what happens if you till or don't till. Live with the decisions that you have to make in that field. If you have to till under some weeds, if you have to break up a crust on the surface, that's up to you. However, it does cause different issues with how you get into a field and how water moves into the soil. So this is at our research station, actually, and this was a field that was tilled. All we're doing is irrigating. Over here, we had a cover crop project, so it hadn't been tilled. And if you look and walk over there, just a few minutes after this irrigation has passed over it, all this water is sitting on the surface here. This was under no-till for maybe 9 months. It hadn't been tilled. That's how quickly these root channels and that structure reformed in a sandy soil. I'm not saying this would necessarily happen in a clay soil. We have very sandy soils at the beach at Carville. But you can see how much this water ponds here. So what's going to happen to that water if it doesn't enter your soil? It could run off. It could evaporate. You need to get water into that profile. You remember what happened this summer when it dried out and we didn't have the water down and deeper in that profile of the soil. If you can infiltrate the soil and get water in, it's there later for storage if you do have a drought. And most of our rain is going to happen spring and early summer here, unless you're really lucky or you have irrigation. But this causes a different problem. We could plant in this field a lot earlier than we could plant in this one, just because that structure also helps provide, it has a great ability to hold equipment as well, because it's similar to have a building in there. So if you have something like this, look how dry the soil is on either side. It does look like the beach there. And look how much that water is ponding just from a little bit of irrigation. And this soil is dry. It should suck it up, but it can't. The rate of water being added is greater than infiltration rate, and we end up having water move along this and create gullies and ditches in the soil. Again, you have to till it. I'm not saying it's right or wrong or good or bad. It's all about decisions people have to make. But at least understand what might be happening here. If later in the season you're like, well, I don't have any water storage, I don't have any water deeper in the profile, I can't get it in, well, this could be a good reason why. So when we talk about, infiltration is letting water into your soil. And then we also have to talk about how do you drain a soil. And it's good, all these different things we talked about in terms of pore space and water movement, all tie back into ditches and into drainage tile. Because what a ditch does is create a very large pore in the soil. You don't think about it that way. But if your water table is right in here, it has to move through the soil pore space, which is smaller and slower. If you dig a ditch, what you've created in that soil now is a very large pore space, and if you can get water into it and you can drain it off, if you have that flow, now you can pull water off the soil. The problem with a ditch is, if you think about the matrix potential of the soil, the ability of that soil to hold water, it's only going to carry off water in the saturated zone. So if you have saturation, there's too much water in the soil for it to hold. It can go into this larger pore, and then if that ditch drains off, you keep removing water. But it doesn't remove water at field capacity, which is good. It's still behind for plants, but you have to consider, what does a ditch do? It drains off saturated water. It doesn't drain off field capacity water, which in some cases might still be too high to get equipment out there. So it's not a miracle worker. What it does is help lower this water table, and it creates a very large pore to drain water off of there. And it's the same thing with tiles. You don't put your tile above where the water table's at. It's not going to help you. It doesn't matter if your soil is at field capacity and it's very wet. It can't get into the tile because the tile is a large pore. And that smaller pore is going to hold on to water more tightly. So you actually end up with water is going to stay in the soil instead of going in the tile. It's only going to drain out. The same thing right here. If you think about clay is not going to move, water's not going to move from clay into sand unless it's saturated. It's the same thing with a tile. That's a very large pore right there. You have to have saturation for it to move in there. So this is, has anyone ever watched the videos in class where they show water moving through a soil? Those are hard to find now. So this is from Cornell's Soil and Water Lab. And it's a really good image to show you all the different properties that we're talking about. So here's your clay, silt, and sand over 15 minutes. Sand has larger pore space. Water can move faster, so it infiltrates faster. The same thing we're talking about with those structural pores. If you can have those macro pores in the soil, water is going to move a lot faster through there. Water doesn't move as fast through clay. So infiltration, movement of water, is better with large pores. However, it can cause different issues depending on where it is in your soil. So this gravel here, think of that as a macro pore. The surface, the atmosphere, is an incredibly large pore. So you're going from a large pore into a smaller pore. So water can drain into that gravel faster than it can into this silty soil. So where does it move? Straight down to the gravel, and then it starts moving laterally across the soil. But if you look at where the gravel is buried in the soil, you're going from a small pore to a large pore. Those matrix forces in that soil, the way it can hold on to the water, it moves across the top of the gravel until it fully saturates this and then moves in. So the gravel in here is very similar to having a tile. You have to have saturation. You have to have saturated conditions for it to move into this, and then it starts to drain your soil. So it's a great drainage tool for saturated conditions, but not if you're right at saturation. It can't get in there because the soil can hold it stronger than it can move into a larger pore space like that. So, in summary, I wasn't sure how long this would take me. We're not doing too bad. In summary, soil water is negative. You see those negative numbers, the negative 1,500, the negative 0.33. Any of those tools we use to measure soil water, we usually talk about tension or suction or tensiometers. All those numbers are negative because we're talking about lower energy, a drier soil. Water wants to move to negative areas. So soil is always going to have a negative value. If it's positive, you know it's super saturated. Texture is important, mostly for water holding. If you look at those soil horizons in the survey and you see an increase in clay, you can assume it holds more total water. But you also have to start considering that it might hold more total unavailable water at the same time. So small pores hold more total water, but they also hold it tighter, and plants don't have as great of access. Texture and structure combined are good for drainage. So if you're trying to talk about infiltration and drainage in the soil, you can't change how much total water it holds. You can't change that texture. Your texture can report to people, why does a sandy soil drain faster than the clay soil with larger pores? That makes sense. But then the structure is the one thing that you can change to improve movement, at least at the surface of that soil. You can increase the infiltration rate. You increase the water moving in. And if you have storage down deeper, you can get into that horizon